I welcome you all in this lecture on system transfer functions, and this is a sub module for the course on modeling and simulation of dynamic systems, which you are going through. Now, in this chapter on system transfer functions, basically what we would like to do is that we would like to find out the ratio of say output by input say for the second order dynamic systems, okay, and then based on that ratio what we define as the transfer function of the system, okay, and using that ratio we may try to predict or we may try to find out the output of the system for the given input and the transfer function. So, that is the ultimate aim of it. Okay. So, suppose if I am talking about a simple amplifier, for that amplifier we know that suppose there is certain input y t to the amplifier and there will be certain output from the amplifier for this given input depending on the gain of the amplifier, and this gain is defined as output by input. Okay. The physical meaning for this equation, that is gain is equal to output by input, is that if the gain of an amplifier is 5, then for a given input of say 4 millivolt, the output is going to be 20 millivolt. Okay. So, this is what is the meaning of this relation, but for many systems the relationship between output and input is not algebraic form as here or as we can conclude from this one. So, these relationship rather than in the algebraic form, these relations are in the form of differential equation, okay, and due to that the above formula, that is output of gain is equal to output by input, that cannot be applied because these differential equations describe how system behaves with time. Okay. These are not algebraic equation, all right. So, there has to be a certain some way to convert these differential equation into the algebraic equation, and so that we can do the manipulation, that is we can find out the ratio of the output and input. Okay. So, these differential equations can be converted into an algebraic form using Laplace transform. Okay. And what we say that the conversion has taken place from the time domain to S domain. Okay. Time domain means usually differential equations are written in the time domain, and of course, the Laplace transform is carried out in the complex domain or what we call it as the S domain. Okay. So, the transfer function can be defined as ratio of Laplace transform of output divided by Laplace transform of input. Okay. So, this way we can define the transfer function. So, here for algebraic equations we describe the transfer function rather than describing the gain. There the gain has been output by input, and here on a similar logic we define the transfer function as Laplace transform of output divided by Laplace transform of input. Now, signal in time domain are indicated by f, that is f t, that is function time, whereas signals in Laplace domain are indicated by capital F. For small f here we are writing the capital F, and for t here we are writing small s, indicating that it is in the Laplace domain. So, this is the convention followed globally for writing out of the Laplace domain. So, here you can see that suppose we have a transfer function say G s, and input to the transfer function is y s and output for the transfer function is x s, then we can define this transfer function G s as ratio of x s and y s. Okay. So, of course, this is valid for a linear system, and as I said, if the linear system has Laplace transform y s, that is the input to the linear system has Laplace transform y s, and output of the linear system has Laplace transform x s, then we can define the transfer function G s as x s upon y s. And of course, here when we are defining the transfer function, one thing which we always need to keep in mind, that we are assuming all the initial conditions to be 0. Okay. That is the 0 output with 0 input condition. Okay. Now, let us take an example of the transfer function. Okay. So, here I just take a simple spring mass damper system. Let this end of the spring and damper is anchored to the ground, and other ends are anchored to the mass. Okay. And here say stiffness of the spring is K, and the damping constant of the damper is say C, and let the mass be small m, and a force F is being applied here. Then as we have seen that we can draw the free body diagram of the mass, we can find out the unbalanced forces, and then we can equate it to the inertial force, that is mass into acceleration, and we get the dynamic system equation. Okay. That is m dx square x by dt square plus c dx by dt plus kx is equal to F. Now, remember, in this expression F is my input, that is the force, and the output are x. Now, in this case you can see that this governing equation is a second order differential equation which depends on time. Alright. So, in this case we cannot define the gain, but rather we have to define the transfer function. Okay. And to define the transfer function, what we have to do, we have to first take the Laplace transform, and for this the Laplace transform will be m s square x s. We will be discussing about the Laplace transform in coming slides, then I will explain you the detail about how we get this term. Okay. Plus this c into Laplace transform of a derivative is given by s times Laplace transform of x s, plus k, this Laplace transform for this x is x s, and the Laplace transform for force is F s. Okay. So, where these x are actually the function of time. Okay. So, this is the Laplace transform, and from here I can define the transfer function G s as Laplace transform of the output, which is x s here, that is the displacement of the mass, divided by the Laplace transform of the input, which is F s here. So, if I take x s upon F s, so this is what I am going to get 1 by m s square plus c s plus k. Okay. So, this is how this is what we define the transfer function for a second order system. Likewise, we can define the transfer function for a first order system. Okay. So, that one example I will be taking at the end of this lecture, we will be taking an example. Now, before we proceed, let us study a little about the Laplace transform. Okay. This method is very popularly used for solving linear differential equation. The Laplace transform method is used for solving the linear differential equation. using Laplace transform we can convert functions such as say sinusoidal, exponential into algebraic function of a complex variable s. Okay. And differentiation and integration operation can be replaced by algebraic operations in the complex plane. So, this is the advantage of Laplace transforms, that we can do the differential and integral operation as a algebraic operation in the S domain. And you know that we are much familiar with the algebraic operations rather than the differential and integral operations. Okay. So, this way is very convenient for us. Coming to the advantage of Laplace transform method, there are certain basic advantages which we cannot draw from other method. These are: it allows use of graphical techniques for predicting the system performance without solving system differential equation. That is one of the big advantage of this Laplace transform method, that is you need not solve the differential equation, but there are certain graphical techniques, okay, and you can use those graphical techniques to predict the system performance, okay, without solving the system differential equations. Secondly, when we solve differential equations using this method, transient and steady state components of the solution can be obtained simultaneously. You I hope you remember when we were studying the behavior of the second order system, then what we did initially, we studied for the transient behavior separately, and then we studied for the steady state behavior separately, and then our general solution was the addition of both the behavior, that is the transient behavior and the steady state behavior. But using Laplace transform method, okay, we can analyze both the behavior simultaneously. That is also one of the biggest advantage of this Laplace transform method. So, let us see what the Laplace transform is. Okay. So, let f t be a function of time, f be a function of time t such that f t is equal to 0 for t less than 0, that is for the time value less than 0 the function value is 0, and s be a complex variable. Then we can use this Laplace operator, this symbol as operational symbol indicating the Laplace transform of the function, okay, and the Laplace transform of a function f t is given by this one. So, this is how it is written: Laplace operator of f t is equal to f s, okay, that is when I am taking the Laplace, I am moving from time domain to the s domain, and this is integral 0 to infinity e to the power minus s t dt, and this is being operated upon function f t, okay, or this can be written in a simplified way as 0 to infinity f t e to the power minus s t dt. So, this is what we mean by the Laplace transform. Okay. Now, the process of finding the function f t from the Laplace transform, that is the inverse. We are given the Laplace transform and we want to find out the function which is a function of time f, which is a function of time t, okay, and this method is called inverse Laplace transform, okay, and this is represented by Laplace operator to the power minus 1, and this is what we call it as the inverse Laplace transform. Okay. And the inverse Laplace transform can be found from say Fs by inversion integral as here Laplace inverse of Fs, and of course, this will be giving us a function in the time domain. Okay. So, this Ft is 1 by 2 pi j plus c minus j infinity to c plus j infinity integration Fs e to the power st ds for t greater than 0. Now, here in this expression c is the abscissa of convergence and it is a real constant and is chosen larger than the real part of all singular points of Fs. Okay. There are other simpler way of finding out of the Laplace inverse of the Laplace transform that we will be seeing later. So, let us see the basic Laplace transform for the common input. Okay. Suppose first we have the unit impulse at time t is equal to 0. So, here if I plot the size versus function of time t, so here at 0 time I have got a unit impulse. Okay. So, the unit impulse at t is equal to 0 has got a Laplace transform of 1. Okay. Similarly, I can define a unit step signal defined by say 1 t is equal to 0 for t less than 0, here this is 0 and this value is 1 for t is equal to for t value greater than 0. Okay. So, the Laplace transform for this will be given by, I can put this in the definition of the Laplace transform, 0 to infinity integral 0 to infinity e to power minus st dt, and if I carry out the integration I get the value as 1 by s. Next, we can find out the Laplace transform for a unit ramp function. Okay. Now, this is how we define the unit ramp function f t is equal to 0 for t less than 0 and f t is equal to t for t greater than or equal to 0. Okay. So, the Laplace transform for this unit ramp t will be again here we put 0 to integral 0 to infinity t e to the power minus st dt, and if you carry out this integration, of course, here you have to do the integration by part and you will be getting 1 by s square. Similarly, we can carry out find out the Laplace of unit amplitude sine wave signal. So, if we have a unit amplitude sine wave signal, that is f t is equal to 0 for t less than 0 and for t greater than or equal to 0, f t is given by sine omega t. Remember, here I am taking the amplitude say a as 1. Okay. So, if I do this, the Laplace transform of sine omega t given as f s, and this will be, we can again put in the definition of the Laplace transform, and if we evaluate, we are going to get omega by s square plus omega square. Likewise, we can find out unit amplitude cosine wave signal. Okay. So, for cosine wave signal I can find out Laplace transform, that is I define the cosine wave signal f t is equal to 0 for t less than 0 and for t greater than or equal to 0 we have this as cos omega t. Okay. So, the Laplace transform for this will be f s 0 to infinity cos omega t e to the power minus st dt, or this is s by s square plus omega square. So, this is how we can evaluate the Laplace transform. Now, there are certain basic rules in working with Laplace transform, and these rules are the Laplace transform of say a constant a into f t is going to be equal to the a times Laplace transform of f t, that is f s. Okay. Likewise, Laplace transform of say sum of two functions f 1 t and f 2 t is equal to summation of the Laplace transform of f 1 t plus and the Laplace transform of f22, that is the FUS, F1s plus F2s. Laplace transform of first derivative of a function can be found out. Laplace transform of dft by dt is equal to sfs minus f0, but as I said, for the transfer function we assume all the initial conditions to be 0, that is why we can take this f0 to be 0. So, the Laplace transform of a derivative is given by s into fs. Okay. So, this is what we have seen in that example of the spring mass damper system. Okay. Similarly, I can define the Laplace transform of d square ft upon dt square. So, this is given by s square fs minus s f0 minus d by dt at d by dt of f at t is equal to 0. Okay. Again, as I said, we assume that initial conditions are 0, then for evaluation of the transfer function, the Laplace transform of d square ft upon dt square will be given as s square fs. The Laplace transform of an integral of a function can be written as fs by s. Okay. So, this can be evaluated, one can verify that. Then as I was telling you, inverse Laplace transform, that is, if you are given the Laplace transform, that is the value of the function in S domain, and if you are interested in finding out the value of function in the time domain, then we can take the inverse Laplace transform. Okay. And that we can find out some of the standard values of the inverse Laplace transform are given here. 1 by s plus a is the inverse Laplace transform is e to the power minus at here, and if it is a by s plus a, it is 1 minus e to the power minus at. Similarly, if it is b minus a by s plus a into s plus b, it is e to the power minus at minus e to the power minus bt. S by s plus a whole square. So, it will be 1 minus at into e to the power minus at. Similarly, for a by s square into s plus a, it is t minus 1 minus e to the power minus at upon a. Okay. So, this way we can find out the inverse Laplace, we can define the inverse Laplace transform, and we can find the values for some of the standard functions. All right. Now, many times here we may have the denominator, either we will have the quadratic term or the cubic term. Okay. Then in that case, what we do is that basically we resolve that equation or we rewrite that equation in the form of some partial fractions, and then we find out the inverse Laplace transform. Okay. Now, as I promised you at the beginning, we will take up an example of say first order system, and we will try to find out the transfer function of the first order system. Okay. So, our first order system is defined by this expression, as I was telling you that we have the a1 dx by dt plus a0 into x is equal to b0 y. Now, here this y is my input and x is my output. Okay. So, as I was telling you that the Laplace transform we take in the Laplace transform all the initial conditions to be 0 when we are interested in finding out the transfer function. Okay. So, to do that I can just take say the Laplace transform for this one. So, this will be a1 into s times xs plus a0, this will be xs, and this is b0 and ys. Okay. So, from here I can get the output by input xs by ys as B0 divided by A1s plus A0. So, this is what is here. We have B0 by A1s plus A0, okay, and this xs by ys is my transfer function. So, this is my transfer function, okay, and further what I can do is that I can divide the numerator and denominator by A0. So, what I get B0 by A0 divided by A1 by A0 into S plus 1, okay, and say what is my B0 by A0? This is basically the ratio of output by input in steady state condition, because in steady state condition this term will be 0. So, my B0 by A0 will be basically x upon y, of course, in the case of steady state, all right. So, this is my say gain G in the steady state, and this A1 by A0 is the time constant of the system. So, this can be written as tau s plus 1. Okay. So, this way we can find out the transfer function for the first order system. Now, when this first order system is subjected to unit step input, okay, that is I am given the value of ys as 1 by s, then I can find out what is my output, that is what is my xs. Okay. So, from here I can find out xs is equal to gs into ys, or xs is gs, I know g by tau s plus 1, and the Laplace transform of a unit step input is 1 by s as we have seen. So, into 1 by s. So, this xs I can write as g into say I divide numerator and denominator by tau. So, g into 1 by tau divided by s into s plus 1 by tau. So, this is what I can get, or this xs is g 1 by tau divided by s into s plus 1 by tau, and if I take the inverse Laplace transform for this, I can write x, which is a function of time, as g into 1 minus e to the power minus t by tau. Okay. So, this way what I have done is basically that I have solved this first order differential equation using the transfer function and using the step input. Okay. So, using the transfer function and step input, I have found out the time response of the function, or say solution of the equation. We can take the example of a physical system, say a resistor capacitor system here. Okay. Now, in this case say resistor is represented by R and capacitance is represented by C, and say the applied voltage is V, and my interest is to find out the voltage Vc is the Vc, that is Vc is the voltage across the capacitor. So, that is my output. Okay. So, using the Kirchhoff's voltage law or Kirchhoff voltage law, I can write the system equation as this one. Okay. That is the loop equation for this loop. The V is equal to this voltage will be CR dVc by dt plus Vc. Okay. So, this is the transfer, this is the dynamic equation for this first order system, and then I take the Laplace transform of both the sides. So, Vs is equal to CR S Vcs plus Vcs, and then from here I can find out the transfer function, that is Gs is equal to output, that is VCS by input Vs, and this is 1 by Cr into S plus 1. Okay. So, this way we can find out the transfer function for the first order system. And what is the use here, what is the use of this transfer function is basically that we can see say by seeing the or measuring the output, okay, output as a function of time, fine, for the given transfer function and the input. Okay. So, that we can do, either we can take example of any first order system, say hydraulic system or say thermocouple, and we can work out the time response, as here we have seen in the previous case. So, the application of this transfer function is that for a given differential equation we can find out the output response without solving the differential equation. Okay. So, using the Laplace transform we convert that differential equation into in the form of an algebraic equation, manipulate that algebraic equation, and then we convert it back those algebraic equation in the S domain into the equation in the time domain using inverse Laplace transform. So, this way we can use to find out the response of the system. So, if you want to further read it, these are the two references, Mechatronics by Bolton and Modern Control Engineering by Ogata. You can refer it. Thank you.